So, Lewis structures, what are they? They're a simplified representation of valence shell electrons in a molecule. And valence shell electrons are the electrons in the outermost shell of an atom, and they're the electrons that atoms share when making covalent bonds. So you calculate the number of valence electrons in a molecule or a compound by finding the valence electrons number of the individual atoms in the molecule and adding them together. So, for example, CH4, carbon has a valence electron number of 4 right here on the periodic table, and hydrogen has a valence electron number of 1, and then you multiply that by 4 because there's 4 hydrogens in that compound, so that ends up being 8. And an important rule to know when making Lewis structures is also the octet rule, and that is the principle that atoms tend to gain, lose, or share electrons to achieve a stable configuration with 8 electrons in their outermost shell. And so the noble gases have full valence shells, so they fulfill the octet rule automatically, and they're stable. And the one element that does not need to fulfill this octet rule is hydrogens when bonding, because all they need is a single bond, so I think it's called the duet rule. So a hydrogen can just be bonded to a carbon like that, and while the carbon will need to fulfill an octet rule and end up having 8 electrons, the hydrogen only needs 1. And so then some tips for Lewis structure drawing. A line represents a bond, and so one bond is 2 electrons because atoms each give / share like 1 with the other, so that ends up equaling 2. And then each dot represents 1 electron, and each letter represents an atom, so like C for this right here is carbon. And then here's like right here is a little example of what that will look like. And then so Lewis dot structures, the steps to drawing them. First, you're going to calculate the total number of valence electrons, which we learned how to do just now. And so if the molecule is negatively charged overall, like for example, if it was like NH and then like had a plus up here, you would add an electron to the total number of valence electrons, and I'll explain this later in the video. And then if the molecule is positively charged, you would subtract an electron, and that's because if a molecule has a more negative charge, it means that it has more electrons since they're what's negatively charged, and then if it's positively charged, it has less electrons. So the second step is write out the skeletal structure. So hydrogen atoms always go in terminal positions, which is like right here. It's in the outer part of the structure. And then the least electronegative atom goes in the center. And then you want to place a max of 4 atoms around a central atom. So 1, 2, 3, 4, because as we learned about the octet rule, you want to have 8 electrons per atom. And there are special cases, but just for the basic Lewis structures, all you have to worry about is having 4 bonds to 1 atom only. And then third step, you want to distribute the rest of the electrons. So you first will connect all the atoms with single bonds, and then you second place electrons as lone pairs on terminal atoms. And you third want to place leftover electrons on a central atom, and that's like the final spot you'll be distributing electrons. And then fourth, check that the octet rule is satisfied for all atoms. So if the octet rule is not met, you need to make double or triple bonds, and all of these steps are about to be explained further through the example. Okay, so first example. We're going to calculate the valence electrons first, and we're working with CO2, carbon dioxide. Okay, so first, to find the total number of valence electrons, we see that carbon has 4 here, and oxygen has 6, and so 4, since there's only one carbon, plus 2 times 6 plus 12 is 16 total valence electrons. Now we go to write out the skeletal structure of CO2. So we're going to put carbon, the least electronegative atom, in the center, and we're going to put the more electronegative atoms, which are the oxygens, on the outer sides. And to make the skeletal structure, you have to bond all the atoms together. And so we start off with our single bonds here, 1 and 2. And then we move on. We have now the skeletal structure, and so we're going to distribute the electrons to create octets. And so right now, 4 out of 16 of the valence electrons have been used in the skeletal structure to bond the atoms together. So 2, 4. And then this means there's 12 more that need to be distributed. So we have 2, 4. We're going to go 6, 8, 10, 12, 14, 16. And so we now have reached the we now have reached the 16 valence electrons. But if you notice, the octet rule is actually not met because carbon right here only has 4 valence electrons when it needs to have 8 valence electrons. And so, our fourth rule. Check that the octet rule is met. We know it hasn't been met. So we need to make double bonds to fix this, and in other cases triple bonds, but for this case double bonds, because we need to add 4 more electrons to the carbon. So what we do is we take these 2 of the lone pairs from each side and we move them down here to create another bond. And this is what gives us our double bonds. And now you can see that this fixes the problem because both the oxygens still have 8, 2, 4, 6, 8, and now the carbon has also 2, 4, 6, 8. So not only are the oxygens happy, but the carbon is also happy because they are fully stable with the 8 valence electrons. And so the final answer is this. Now, here's some takeaways. So the steps are these takeaways, mainly because if you follow them, you are going to be at least on the right track to making a Lewis structure and most likely correct. But sometimes it does take a couple of tries when you're learning to make sure you gain the skeletal structure correct, and then also just learning like when to use triple bonds, when to use double bonds. But eventually as you practice more, you'll understand it. And then some practice problems. And I'm going to ask you to pause the video and you can use them if you want. And then, so if you paused it by now, here are the answers. So I'll just walk through them kind of quickly. For this first one, NH4+, so here's where we learn about that thing we learned about the valence electrons comes into play when there's an outer charge on the compound or molecule. And so the valence electrons would normally just be 5 for the nitrogen plus the 4 hydrogens is 4 times 1, so plus 4. But in this case, we're subtracting 1 electron, 1 valence electron, because we have a positive charge, a 1 plus charge. And so what that means is that we have 1 less electron. And so since we have 1 less electron, we want to subtract 1, and we end up with 8 here instead of 9, which actually, if you're thinking about how when you draw a Lewis structure, you kind of want the numbers to be even, honestly, it makes sense that this compound goes down to 8 for your valence electrons because it makes it easier to draw. And so here we put nitrogen in the middle because you didn't have to think about which one was more was less electronegative because the hydrogens always go in terminal positions. And then if you count it out, 2, 4, 6, 8, all 8 electrons were used, and the nitrogen has the octet rule met. So that one is finished. And then the second problem, N2. So the amount of valence electrons was nitrogen has 5 valence electrons on its own, so we multiply that 2, we get 10. And this one is a little trickier because it does have a triple bond, but you'll find out that, so we first start out with like trying it out. We have 2 and then 4, 6, 8, 10, and you think, oh, that doesn't work, so let's try putting them equal on that side, but still that doesn't reach the octet rule. So what we're going to do is move this down here and move one of those down here. And now let's check. Let's just erase that. We have 2, 4, 6, 8. Oh wait, sorry. 2, 4, 6, and then 8, 10. So that fills the rule. And then lastly we have H2O. Amount of valence electrons is 8. Then we put oxygen in the center because hydrogens always go in terminal positions. We distribute our electrons, and that's the answer you'll get.